Hello, welcome to Civil Engineering with Amir. In the previous videos, we solved 15 examples on the topic of shear force and bending moment, and I explained how you can use the method of sections to cut the beam at different sections, write the shear force and bending moment as functions of x, and using those functions, we were able to draw the shear force and bending moment diagrams. Now in this video, I'm going to go over the basic concepts and principles of the graphical method and explain how you can draw the approximate shear force and bending moment diagrams without having the shear force and bending moment as functions of x. So in the first few minutes of this video, I'm going to talk about the sign convention I prefer to use to determine my shear and moment. Then I'm going to explain why we prefer to use the graphical method sometimes instead of the method of sections. I'm going to go over the main principles of the graphical method. And finally, I'm going to explain how you can draw the shear force and bending moment diagrams for a simply supported beam under basic load conditions. So we have a simply supported beam with a total length of 6 meters, and then we're going to apply different concentrated loads, concentrated moments, rectangular load, triangular load, and trapezoidal load, and explain how we can draw the shear force and bending moment diagrams for each case using the graphical method. Alright, let's start with the sign convention. If you watched the previous videos, you know if we cut the beam at any point along the beam, for example this point C, we're going to have two cut segments. And by writing the equations of equilibrium for any of these two cut segments, we can determine the internal forces at that cut section. Now, before we start our analysis, we have to establish a sign convention to define positive and negative values for these internal forces. For example, in the sign convention I always prefer to use, when I'm analyzing the left cut segment, my positive shear acts downward, my positive moment acts counterclockwise, and my positive normal force acts to the right. Now, based on this convention, I know the internal forces on my right cut segment must have the exact equal values as my left cut segment, but the directions are exactly the opposite. So, for my left cut segment, the positive shear force acts downward, the positive moment acts counterclockwise, the positive normal force acts to the right, and for the right cut segment, the positive shear force acts upward, the positive moment acts clockwise, and the positive normal force acts to the left. Now the most important thing here is, whatever direction you're using for your positive internal forces on the left cut segment, you have to use the exact opposite directions for your right cut segment. For example, someone may choose the upward direction for the internal shear force of the left cut segment, so they have to use downward direction for the right cut segment. And if they're using the clockwise direction as the positive direction for their moment of the left cut segment, they have to use the counterclockwise direction for the other side. So it really doesn't matter what directions you're using, as long as you're using opposite directions for your two cut segments. And once you define your sign convention, try to remain consistent and follow the same sign convention throughout your problem. Again, these are the positive directions or the sign convention that I always use, and it's widely accepted in many structural engineering textbooks, like Hippler's structural analysis. Now, the reason I like this sign convention is that when I'm drawing the shear force and bending moment diagrams, the positive shear force and bending moment values will show up at the upper portion of my y-axis. Alright, now let's talk about why the graphical method makes our lives easier sometimes. If you consider this simply supported beam, we have a pin support at the left end, and we have a roller support at the right end, And we have different types of loadings applied to this beam, including concentrated loads, concentrated moments, triangular load, and rectangular load. Now, if we want to draw the shear force and bending moment diagrams for this simply supported beam using the method of sections, we have to determine the support reactions and then cut the beam at different sections and determine the shear force and bending moment as functions of x. Now, using the method of sections, since we have several loads applied along the beam, wherever the loading changes or wherever there is a discontinuity, we have to cut the beam at those sections. So we're going to have one section here, another one here, another one here, another one here, one here, one here, one here, one here, and one here. So we have to cut the beam at 9 different sections and determine the shear force and bending moment functions for each cut section. So we're going to end up having 9 different functions for our shear force and 9 different functions for our bending moment. And then for each section, using those functions that we determined, we will be able to draw the shear force and bending moment diagrams, which can be a very tedious and time-consuming process. So in the similar cases, when we have several concentrated point loads and several concentrated couples and distributed loads, we need to learn a simpler method or graphical method to be able to draw our shear force and bending moment diagrams without having to determine the shear force and bending moment functions in terms of x. Now, in this simpler method, there are a few principles that we have to follow. I'm going to explain what those principles are, but I'm not going to get into theories, because almost all structural analysis, statics, or mechanics of materials textbooks explain where these principles come from and the theory behind them. So I'm not going to get into those theories. I'm just going to mention what those principles are and how we use them. All right, so the first principle is if we have a distributed load between 2 points along our beam, for example, these 2 points, the change in shear between these 2 points will be equal to the area under the distributed load between those 2 points. So the delta V between these 2 points will be the area of this triangular load. Or if your distributed load has a more complicated function, you can use integration between those 2 points. And the second principle is the slope of shear diagram at any point between these 2 points where we have a distributed load will be equal to the intensity of distributed load at that point. So for example, if the intensity of the distributed load is 5 kilonewton per meter here and 0 here, the slope of our shear diagram at this point will be equal to 5, and the slope of the shear diagram at this point will be equal to 0, or the derivative of V with respect to x will be equal to W. Now, the very important thing here is we can't use these 2 principles at points where we have a concentrated load. So, for example, we have a distributed load here between these 2 points, but we can't say that the change in shear force between these 2 points is equal to the area under this distributed load, because we have this concentrated load somewhere in the middle. In these cases, when we have a concentrated load, if our concentrated load is upward, we're going to have an upward jump in our shear diagram. And if our concentrated load acts downward, we're going to have a downward jump in our shear diagram. So for this situation here, for example, we can determine the change in shear between these 2 points. Then at this point, we're going to have a downward jump in our shear. And from this point to this point, we can determine the change between these 2 points by calculating the area of the distributed load between these 2 points. I understand that it may be a little bit confusing now, and you don't have to memorize everything at this stage. In this video and in the next few videos, I'm going to solve different examples with different situations, different types of loadings. And by practicing those examples, I'm sure you'll understand what's going on here and you can review these principles whenever you get stuck while solving those problems. So just bear with me now and don't get overwhelmed, don't panic. I know there's a lot going on here, but the best way to master these principles is by solving different kind of examples and by practicing. All right, so we explained the first two principles. Between any 2 points, if we have a distributed load and if we don't have a concentrated load applied in between, we can say the change in shear is equal to the area under the distributed load, and the slope of the shear diagram at any point is equal to the intensity of the distributed load. Now, the next two principles are very similar to the previous ones. The third principle says that between any 2 points, the change in moment is equal to the area under the shear diagram between those 2 points, or delta M is equal to the integral of V dx. And the fourth or last principle says that the slope of moment diagram at any point is equal to the intensity of shear at that point, or the derivative of our moment with respect to x is equal to our shear. And we have the similar exception here. Between any 2 points, if we have a concentrated moment, we're going to have a jump in our moment diagram. For example, at this point, or at this point, we're going to have jumps in our moment diagram. For clockwise moments, we're going to have an upward jump. And for counterclockwise moments, we're going to have downward jumps in the moment diagram. And these directions that I mentioned here are all based on the sign convention I chose and explained to you at the beginning of the video. So based on this sign convention, if we have an upward concentrated load at any point, we're going to have an upward jump in the shear diagram. And if we have downward concentrated loads, the jump in our shear diagram will be downward. And again, based on this sign convention, a clockwise concentrated moment will cause an upward jump in our moment diagram. And a counterclockwise concentrated moment will cause a downward jump in our bending moment diagram. All right, now we talked about the sign convention. We talked about why we need to learn this graphical method. I explained the 4 main principles we use in this graphical method. And now it's time to practice drawing the shear force and bending moment diagrams using these basic concepts that I explained.